So as far as in this particular case is concerned, so if you see, so there is a kind of a measurement. So if there are three parts are involved in it. So one is a kind of a measurement fluid inlet. So and then there is going to be a silicon die with a diaphragm, and then there is a constraint base which is available, and then there is a kind of a measurement fluid inlet which is available. So in this case, so what we are trying to do is, so this is a kind of a backside pressure which exhibits, that is through this cavity a backside pressure is getting generated, whereas this is a kind of a configuration where there is a kind of a front side pressure exists. So in this front side pressure, what we have is, we have a measurement fluid which is kept as an inlet, and through this inlet, through a pressurized pressure, so the cavity can be used for the pressure within the cavity can be efficiently used using this system. So this is a very good example of developing a kind of a micro pressure sensor. Now as far as in this etching process is concerned, the etching process is classified into two. One we call it as a wet etching process, and the other one we call it as a dry etching process. In the case of wet etching process or dry etching process, we can classify it as isotropic etching and anisotropic etching. However, in the case of a dry etching process, we have the plasma etching or we have the deep reactive ion etching. Let us discuss in detail about the different types of etching. Now let us talk about the wet etching process. So this wet etching process, it is also called as a chemical etching process, as it involves a kind of a solution, either it might be with dilute chemical which is or certain amounts of acid to dissolve the substrate. Let us take an example. So let us take a dilute hydrofluoric HF solution which is used to dissolve SiO2 and Si3N4 and polycrystalline silicon, whereas a potassium permanganate is used for etching the silicon substrate. So what we are trying to do over here is, so we need to create such structure. So in order to create this structure, so initially we are depositing with a photoresist over the substrate, and then a fresh etchant is made to pass through this reaction, so that it reacts with the photoresist, finally ending up in a byproduct, and then we get a structure as mentioned over here. So it's a kind of an etching which is being performed on this photoresist layer. So if we try to look into the overall mechanism of it, so SiO2 plus 6HF, which will result in H2SiF6 plus 2H2O. So this hydrofluoric acid etches the silicon oxide here, and the byproduct dissolves away the overall content in the water. So the rate of etching typically depends upon the substrate material to be etched, concentration of chemical reactant in the solution, and temperature of the solution. However, the major disadvantage of the wet chemical etching for pattern transfer is the undercutting of the layer underneath the mask, resulting in loss of resolution in the etched pattern, and thus instead of this chemical etching, a dry etching can be explored. So this undercutting is nothing but, sometime here at this curved surface, it might not be a proper cut, it might be a kind of a curved surface which may exhibit. So when a curved surface gets exhibits, what happens is it will have an impact on the devices. This will result in a certain amount of failure in the system. So this kind of process will result in a kind of loss of resolution, and sometimes it may also degrade the functionality of our system. Now let us see the overall classification of this etching process. One set of etching is called as isotropic etching. So isotropic etching process is a process that remove material from the surface in all direction at an equal rate. So that is, if I want to have a curved structure, or if I want to have a structure something like this, we try to pump the etching medium inside it, so that these etching medium will efficiently etch the material, and finally we get a required framework or required structure based on our functionality. This process which is one of the important aspect of this process is orientation is independent of the etching technique, and it is performed for the substrate which is made out of homogeneous and isotropic material, so that in such a way that the material is uniform throughout. And yes, in certain cases, for example, wherever we have a kind of a single crystal structures, etc. In the case of single crystal structures, such kind of isotropic etching will may have an impact. Okay, like for example, in the case of single crystal etching, so these kind of wet chemical etching will have an impact on the overall crystal structure, etc., which can be efficiently eradicated using a dry etching process. However, with the geometrical perspective point of view, or with reference to configuration perspective point of view, these chemical etchant attack the material uniformity, which will be helpful to etch the layer in all the direction. So, one important point of using such kind of isotropic etching process is that you don't need to have a post treatment. So, it is hardly desirable in micro manufacturing because of the lack of control of finished geometry of the workpiece. So, that is, you don't need to worry about a kind of a post processing what we are looking for. Next, when I try to talk about an anisotropic etching, so anisotropic etching is a separative microfabrication technique that aims to preferentially remove a material in a specific direction. Okay, either it might be in a lateral direction or it might be in a linear direction. So, it is used to create a precise shapes like sharp corners, flat surfaces and deep cavities can be easily manufactured using this anisotropic etching process. So, this anisotropic etching process is used to fabricate microstructures such as diaphragm and cantilevers on a silicon wafer. It is also efficiently used to create more complicated 3D microstructures on a silicon chip for applications such as inkjet printing devices and microfluidic systems. So, these are some of the applications of anisotropic etching. Now, when we try to closely observe the key challenges with anisotropic etching, it is slower than an isotropic etching and it rarely exceeds 1 micrometer per minute. So, like it is a kind of stage by stage process which is being evolved for etching a particular etching the surface in a particular direction, and the etching rate is highly temperature sensitive, and usually it requires at an elevated temperature of 100 degrees Celsius in the process, which precludes the use of many photoresistive masking materials. So, this is one of the major challenge of going for an anisotropic etching. Now, let us discuss about the dry etching. So, as far as these dry etchings are concerned, so these dry etching involves the removal of the substrate material by a gaseous etchant without any use of any chemical or rinsing. So, for parts which requires a maximum precision and more control of the shape of the etch geometry, dry etching method is considerable to be the preferred options. Okay. So, as far as in this dry etching method is concerned, a substrate is loaded in a sealed process chamber to produce a plasma under a vacuum of a special process gas. From this plasma, reactive species are created, allowing for chemical or physical interaction with the substrate. So, these obtained species either interact in a chemical manner, reaction with the surface atom, or a physical matter collision with the surface atom to remove the material from the substrate surfaces. Herein, an atom layer by atom layer is removed to ensure a highly controlled etch process. For an even more selective removal of material, dry etching is traditionally combined with the photolithography process. So, these kind of complex combinations of variables in the process chamber allows for steering the process in the maximum precision mechanisms. So, which is considered to be one of the major advantage or the methodology for a dry etching process. So, in the case of a dry etching process, let us take this simple plasma based process. So, in this plasma based process, the process involves adding chemically reactive gases such as CCl2F2 to plasma that contains ion and has its own carrier gas. Basically, it might be an argon, etc. If you try to look into the overall configuration of it, there is an etching material which is available, and then there is a plasma with ion which reacts with the neutral material. So, the reactive gas produces a reactive neutral when it is ionized in the plasma. So, these reactive neutral bombards the target on both the side walls as well as the normal surfaces, whereas the charged ion bombards only the normal surfaces of the substrate. So, the etching of the substrate material is accomplished by a high energy ion in the plasma bombarding the substrate and surface with simultaneous chemical reactions between reactive neutral ions and the substrate material exhibits. This high energy reaction causes a local evaporation, thus results in the removal of the substrate material. So, one of the key point which you may need to consider here is the etching front moves more rapidly in depth direction than in the direction of the side walls. This is due to large number of high energy particles involving both the neutral ions and the charged ions bombarding the normal surface, while the side walls are bombarded by the neutral ions only. So, this is the overall characteristics of a plasma ion etching. So, conventionally, as far as this plasma ion etching is concerned, it is a very slow process. It is at the rate of 0.1 micrometer per minute or 100 Armstrong per minute, and the plasma ion etching can increase the etching rate in the order of 2000 Armstrong per minute. The increase in the etching is primarily due to increase in mean free path of reactant gas molecules in the depth to be etched. So, in the case of a plasma ion etching of silicon substrates is typically faster and cleaner over the wet etching. A typical dry etching rate is 5 micrometer per minute, which is about 5 times that of the wet etching process. Now, some of the key challenges which needs to be addressed are, it is also limited to in producing a shallow trenches as in the case of a wet etching process, because the plasma will try to disperse at different directions, and this may result in certain amount of distractions at the end of the curvature of these particular structures. Second, the process of dry etching is limited in producing MEMS with low aspect ratio. So, the aspect ratio is in the order of dimension per depth, and for plasma ion etching the aspect ratio is less than 15. And most important point is the contamination of the substrate surface by residue is another challenge which exhibits in the case of a plasma ion etching process. Now, let us discuss about a concept of deep reactive ion etching, which we call it as DRIE. Despite the significant increase in the etching rate and depth of the etched trench or cavity that can be achieved with the plasma, the etched wall in the trench remains the wide angle theta at its depth. So, the cavity angle theta is very crucial in MEMS structure and has to be at 0 degrees, especially when comb electrodes in micro grippers, where the face of the electrode must be in parallel to the each other. So, in that particular aspect, such kind of DRE can be efficiently deployed. Now, as far as in this deep reactive ion etching is concerned, so the deep reactive ion etching process produces a thin film protective of few microns on the side walls during the etching process. It involves the use of high density plasma source that allows an alternative process of plasma etching of substrate material and deposition of etching protective material along the side walls. So, these etching protective material are material with a high selectivity ratio such as silicon dioxide, polymers and photoresist are used as a protective material. The working principle of this deep reactive ion etching is almost similar to plasma ion etching. So, the process is effectively increased the aspect ratio from 15 to 30, with currently reports suggest that it has a aspect ratio of 100 and above. So, this is one important aspect. So, as far as in this deep reactive ion etching is concerned, so when we try to classify the different types of etching process. So when we try to make a comparison with reference to a dry etching process and a wet etching process, when we try to consider with reference to directionality, the dry etching, it is good for most of the materials. However, in the case of wet etching, only with single materials with particular aspect ratio, such kind of wet etching can be deployed. As far as process automation is concerned, these dry etching process is good. However, in the case of wet etching process, it is very difficult to deploy a process automation. Now, with reference to selectivity perspective point of view, so it is the dry etching is almost poor. However, with reference to wet etching perspective point of view, its characteristics are quite good enough. And environmental impact perspective point of view, so there are not much residues are observed in the case of a dry etching process. In the case of a wet etching process, there is always a kind of a residue which is left out, which may have an impact on the environmental aspect. Then as far as masking film adherence is concerned, so in the case of a dry etching process, it is not as critical. However, in the case of a wet etching process, it is highly critical. Now, when we try to talk about the materials which we need to be etched, so there are specific materials which are available, which can be only etched using this dry etching process. Like whereas in the case of wet etching process, it has a capability to do all the kind of material. For example, in the case of a dry etching process, in certain cases, if we are using a kind of a brittle material, so it may result in a kind of multiple crack in this material. So this is one important aspect which may affect the overall performance when we try to use a dry etching process for a brittle material. Then with reference to process scale up is concerned, the dry etching process is difficult. However, in the case of wet etching process, it is quite easy. Cleanliness perspective point of view, it is conditionally clean. However, wet etching point of view, it is good to very good. Critical dimensional control is concerned, it is very good. It is less than 0.1 micron, which has which is highly used or potentially used in micro robotics perspective point of view. In the case of wet etching process, this parameter is considered to be pretty poor. And the cost wise perspective point of view, dry etching process is slightly costly compared to the wet etching process. In the case of a dry etching process, you have a kind of a different sub integrations needs to be included in that, so which makes the system more costly. Whereas in the case of a wet etching process, it is bit less expensive because it is more to do with chemical interacting with the material. And the typical etch rate is concerned, the dry etching process is slow. It is in the order of 0.1 micrometer per minute to with a range of 6 micrometer per minute. However, in the case of wet etching process, it is in the range of 1 micrometer per minute and up, so which is slightly faster. And as far as operational parameters perspective point of view, in the case of dry etching process, this has quite a good amount of, there are lots of parameters are getting involved in the case of a dry etching process. In the case of wet etching process, it is very limited only for few characteristics. Control of each rate is concerned, so good in case of slow etch, however difficult it is in the case of a wet etching process. Now, these are some of the process which we had discussed with reference to bottom up and a top down approach. Now, with reference to patterning perspective point of view, or with reference to surface generation perspective point of view, or functionalizing the surface perspective point of view, surface processing play a vital role. So as far as in this surface processing is concerned, so it has nothing to do with adding or dropping the material. It is more to do with functionalizing the surface based on the requirement. So as far as this surface processing is concerned, so while for micro robotic application perspective point of view, two different surface processing techniques are being efficiently used. One is called as a laser processing technique and the other one is called as a plasma processing technique. So as far as this laser processing technique is concerned, most of us are well aware about this laser processing technique. So just to give you a overall understanding as far as this laser processing technique is concerned, we all know that, like, let us consider this as a material. When the light falls on a material, it exhibits three different phenomena. the reflection, absorption, and transmission. Reflection perspective point of view, like let us take a simple mirror, and when the laser hits this mirror, so we will be having a reflection which exhibits over here. Transmission perspective point of view, certain amount of mirrors are bit transparent enough so that when the light falls on it, it tries to transmit to the system. As far as absorption perspective point of view, so when the light hits the surface, the material will try to absorb the laser light, which will result in a kind of a heat transfer which exhibits over here. So this is a kind of a mechanism which exhibits when the laser interact with the material. Now, as far as surface perspective point of view is concerned, like when we try to talk about the laser processing, so the fundamentals of the laser processing can be classified as laser based heating, where a certain amount of heat is generated on the surface to create certain to realize some kind of microstructures or to functionalize the structures based on the requirement. Then laser based melting, third is laser based vaporization, and laser based plasma formation. So PLD is a very good example of laser based plasma formation. As far as laser based heating is concerned, so we can have a laser cleaning process, laser based functionalization process, laser texturing, etc. comes under this particular category. So let us see some important applications where a laser is being used for functionalizing the surface for micro robotic applications. So laser processing it is a highly effective technique for fabricating hydrophobic and super hydrophobic surfaces, particularly when we try to talk about micro robots that operate in an aqueous or in the kind of a humid environment. These surfaces help in reducing the drag. It also improves the mobility and it also prevents contamination. Like in fact, we had discussed about its applications, about micro robotic applications in our first module, where we had discussed these kind of micro robots are efficiently used for surveillance applications or in order to understand the pollutants, etc. And there are different micro biomimicking robots which are being established by different research groups, which has been functionalized in such a way that it has a hydrophobic surface in it, so that through these hydrophobic surfaces the water contamination can be results in a kind of a enhanced water repellency. Okay, so here in order to have a better understanding, we need to have a kind of understanding on the laser material interaction and to create a micro and nanostructures to enhance the repulsion. Now when we try to talk about laser processing, so for this particular course we are limiting only towards generation of hydrophobic surfaces with laser processing. So the technique in laser processing for hydrophobic surfaces concerned, so we can deploy a kind of a pulsed nano or nanosecond laser or a fiber laser for texturing on the surface. It can also create a hierarchical micro and nano structures similar to a lotus leaf structure, and an ultra short pulse laser which minimizes the heat affected zone, which can be used for preserving the material property. It also enables a precise patterning of hydrophobic structure on microscale surfaces, and it is also used to fabricate bio-inspired textured surfaces for microphobic coating. Now with reference to application perspective point of view, like striders are there, micro robotic striders are there, where it's a kind of water walking micro robots. So in these robots we have the major requirement is it should have an enhanced buoyancy and it should have a good surface adhesion control. Second, we can talk about the biomedical micro robots. As far as in this biomedical micro robots are concerned, one of the important aspect which we may need to take it up into consideration, it should prevent from biofouling in targeted drug delivery, as well as in the case of minimally invasive procedures. So by having an appropriate surface structures, so it can prevent the biofouling related aspects. Now, with reference to underwater micro robots perspective point of view, it reduces the hydrodynamic drag and it enhances the locomotion efficiency. So this is one important aspect which is being considered in the case of micro robotic application, especially when we were discussing about the scaling laws with reference to fluid interaction. So the movement of the fluid needs to be appropriately taken care in such a way that these surfaces which are getting generated will help for a smooth locomotion of these micro robotic structures in such kind of functional applications. Next is a self-healing robotic compound. So as and when we try to go on a micro scale, this self-healing plays a vital role, because if the surface of these micro robots has a capability to attract certain amount of particles, it may result in some kind of undulated behavior on these structures. So in order to avoid that, so if these robots are having a kind of a self-cleaning behavior, sometimes it is through coatings or sometimes it is through textures, so that we can maintain a kind of a surface integrity in the case of a harsh environment. Now, as far as these structures are concerned, like this is one demo which I would like to show from our lab, where we have created certain amount of patterns. So in these patterns, if you see, like so we have used a kind of a NDAG laser, but basically it's a kind of a continuous laser which we have used, and these lasers are integrated with the galvano, and the overall wavelength of this laser is close to around 1064 nanometer, and these are some kind of patterns which can be generated out of it. In fact, this video will show you a better clarity. So this is a kind of laser which is used for scanning the surface. So appropriate scanning will be helpful for us to create a textures. So the overall manipulation of these structures are generated using a galvano, which is capable enough in creating a textured pattern on the surface, and these textures are efficient enough in such a way that it takes care of the hydrophobicity, it takes care of the biofouling related characteristics, it also takes care of the overall functionality of it, which will enhance the overall propulsion of the system. Next important processing technique is called as a plasma processing technique. So as far as in this plasma processing technique is concerned, so there is a plasma chamber. So like a plasma is generated by applying a biasing between two different leads. So between these two different leads, when there is a biasing is employed, so a plasma is getting generated out of it. In fact, I can just show a plasma. So where the plasma is a kind of a cloud of a dense material, which will be helpful for us to change the surface property of the material based on the requirement or based on the characteristics. Like, in fact, this is one good example where we had a kind of a small PTFE based structure. So in this PTFE based structures, so there is a kind of a plasma treatment which is being deployed on it. So through this plasma treatment, so the structures were appropriately manipulated, and these manipulated structures has a capability to have different functionality. It has a control over the hydrophobic as well as the hydrophilic transformation based on our requirement. So now when we try to see the mechanism of this plasma processing, so the plasma treatment is a powerful surface modification technique, and it is used to tailor the wettability of the polymers. It enables the transformation from hydrophilic to hydrophobic state. This process is particularly beneficial in applications such as biomedical devices, coatings for micro robots, and microfluidic system. So if we look into the mechanism, see these mechanism of surface modification using this plasma processing. So it is classified under three different categories. One is towards surface roughening, that is towards micro and nano structuring. Second is towards the chemical functionalization, so that in certain applications what we try to do is we try to change we try to change the overall characteristics of the bond structure. By changing the characteristics of the bond structure, we can functionalize these structure. Then one of the important functionality is with reference to cross linking and surface coating, which is possible by inducing certain amount of gaseous region in the plasma process, so that these gaseous region are capable enough in such a way that it will try to realize the process, and these realized process will take care of the overall functionality of the requirement.